Thank you, Soraya. Thank you all for being here. Sure, go ahead and clap. Are you able to hear me in the back? Is it all right? Yeah? Okay, okay. This room is a little funny. I'm glad you found your way here. As Soraya told me, this is our unfinished basement, which makes it sound like we're in someone's house and hasn't figured out how to finish their basement yet. I'm delighted to be here. How many of you are undergraduates?
Wow.
Does on the grade count?
Yes.
Okay.
And how many of you are graduate students? Wonderful. Okay, so we have a preponderance of students. I won't take the time to figure out what the undergrad students are looking to get out of this, but give me a big smile when I talk about something that you're interested in, and I'll talk a little longer about that. Okay, so I titled this talk "Transition to Policy," and I did that because I'm going to tell you about both a kind of research journey of mine and a professional journey that both have this kind of pathway of starting out, as a kind of traditional professor, traditional path, traditional research path, traditional professor path, and then making their way to something connected, but actually rather different. And one of the things that has been exciting to me about being a computer science professor is how many things I've been able to do that I never imagined were within the kind of scope of things that a professor could do. So I'm going to kind of reveal to you some of those, and it's really been something that has kept me energized. One of your professors said he was an old timer. He's been here for 25 years. I've been at Georgia Tech for 30 years. So to be at one place for that long is, first of all, a rarity in today's work world, right? You all are probably expected to change jobs multiple times. So it's a rarity. And it's in some ways a testament to the set of opportunities that you can have as a professor, that you can keep from getting bored while still remaining in the same place. So that's kind of a bit of the punchline. So I'm going to just tell you a little bit about myself. I'll add to some of what Soraya had to say in terms of my biography. And then I'll talk about my research, a particular thread through my research work. And then I'll talk about what I've been doing career-wise, and the punchline of that will be to talk about my National Science Foundation work that I've been doing over the last year. And then I have a discussion topic for you, which I think we probably won't get to, but just in case there's something at the end. Okay, so I grew up in Maryland, in the suburbs of Washington, D.C. I was an undergraduate student at Washington University in St. Louis, and I was a computer science and electrical engineering double major. Comp wasn't really a thing at the time. It was long enough ago that if you wanted to kind of do, kind of compy things, you did some double E and you did some computer science. So I did those. And then when I was finishing undergrad, the job market didn't look very exciting. And so I thought, well, why didn't I stay for a master's degree? And I had a chance to do some undergraduate research. So a professor that I'd done undergraduate research with said, come join my lab for your master's degree. I can fund you. Whoa, that's pretty cool. And I did a master's thesis, and that thesis was in parallel simulated annealing. So this relic on the left-hand side is one of the first commercial multiprocessor machines that you could buy. So a company called NQ built these. This one, the one we had in the lab, had 16 processors, and it used a message passing interface, and I programmed it to run a parallel version of an optimization, a general optimization technique called simulated. So that was sort of my entry point into research. When I was finishing my master's, I was only point, a year into the master's program, I decided, okay, this research stuff is pretty cool, and I really thought I would enjoy teaching, so I decided to stay for a PhD. I switched areas. I switched and worked in computer networking for my PhD, and then I went so rapidly to Georgia Tech, which is part of how I have 30 years at Georgia Tech, and I'm, not in a nursing home or something. So I got started pretty early at Georgia Tech as an assistant professor. I then worked kind of in pretty traditional internet networking. One of the highlights of the work I did, which seems slightly depressing, it happened when I was about 3 years into being a professor. One of the highlights of my research work is that I, with colleagues, developed this graph-based, improved on graph-based models for the structure of the internet. How is the internet constructed? So key elements are, it's a network of networks. So if you're going to have a graph model, you ought to model the separate networks that are then connected to each other. It seems like a dull observation, but at the time people were using things like random graphs to model the structure. So why do you model structure? You model the structure as an input to a simulator that is then going to test out your new idea about, for instance, routing. And you need a topology. You need a network topology on which to run simulations of your new ideas on. So anyway, we improved upon these models. These are, if you don't know, these are screenshots from Google Scholar, which is one of the ways that professors, what's a great phrase to say? Google Scholar is one of the ways that you find out whether people decided they wanted to reference your paper. Okay, so this is the year of the publication. So I was a grad student in the late 80s and early 90s. And then this is the number of citations. At whatever point I decided to pull that screenshot off of Google Scholar. Of course, the numbers, citation counts go up some very slowly, some very quickly, depending on. I then decided to transition to working on mobile networks. The internet was getting kind of, they call it ossified. It's very hard to change anything in the internet by the end of the 1990s. There was such an uptake in dependence on the internet for business, for you all were not born, but some of you were not born. But I'll just tell you, in the dark ages, the internet wasn't that important. It wasn't used for that many critical things, and then in the 90s, that all completely changed. And there's so much business interest, it was very hard to change the core protocols. But things that were happening at the edge, like mobile networks, those were easier to experiment with, and they were easier to change. I then went crazy with breadth in my research interest, and got involved in something we call computing for good. And through that, I went to the West Africa country of Liberia 9 times over a 4-year period, and worked with the Carter Center on supporting mental health clinicians who were working in West Africa, in Liberia, trying to increase the mental health treatment in the country. And I can talk for a long time about that, and if you're interested, I will. I actually lost my old laptop, the screen broke, and I lost my CD, which is a disaster. Disaster. This is where you write down everything you've done in your whole 30-year career. I mean, I'll be able to get it back. But that was I needed that to remember how many PhD students I've had, since I didn't have it. It's somewhere in the 20s. That's why it's a 2x. And I should say, notably, the reason I'm here is that one of my current PhD students graduated from UNM as an undergrad, Beatrice Avar. His parents are both in the audience, and has been my PhD student since 2019. And so I've gotten to know the UNM through Baya and through Soraya. Okay, so that's a little bit of a long story. Let me now tell you about a particular line of work in the area of mobile wireless, and I'm going to show you how some sort of fundamental research questions, and then I'm going to show you how this connects into health. All right, so everybody knows this, right? The quality of your coverage when you're on your mobile phone, it depends where you are. You're, say, in an elevator, it may not work at all. You are, at a concert, it may not work very well. You're in some, standing on the street downtown, maybe great, right? So the quality, you might be standing somewhere on the street and it's great, and you walk around the corner of the building and it's bad. Like, this is crazy, right? It depends. It depends heavily on the location. And in areas with lower populations, it tends to be worse. Why? Because the financial incentives for companies, ISPs, to build out infrastructure into regions where there aren't very many people to pay for the infrastructure, the incentives are not there. So if you go to a region like certain parts of New Mexico, where their populations are sparse, or where people don't have a lot of money to spend on connectivity, you tend to see worse connectivity. This is a sign from the trailhead of a trail in Georgia, and what it says down here is, so this is about what you should do if you have an emergency on the trail, call 911, but also, please note your cell phone may not work in some areas due to tower locations and terrain, right? So if they didn't build the tower in the right place and you're on the other side of the mountain, you may well be out of luck. I have a story to tell about an emergency situation while hiking with students, which led me to be interested in this problem. And so of course we're very reliant, increasingly reliant. And if I said to you, okay, here's the task. Here's your homework, most problem. Go produce a map for some region of decent size, say New Mexico, or maybe something smaller than that. And, color code the quality of the connection, the cellular connection, at every one of those locations. Okay? That's your homework. What would you do? It sounds hard, right? It sounds hard. It sounds like maybe you'd be driving around a lot, and maybe you'd be walking around a lot. Maybe you would do something like say, well, okay, if I could find out where the towers are, and, I could probably get a good start, right? Because presumably the connectivity is pretty good near the towers. So, you might start to try to put together some things like that. So it's a hard problem. So one of the things you do if you want to work in this area is you actually do go collect data. So the vehicle on the right is a rental car, and we are in New Mexico. So Beatrice and I and another student came for Balloon Fiesta. We're not stupid. We came for Balloon Fiesta 2 years ago, and we brought, and you can see, this is a large collection of phones. I think we had 3 each of Verizon, AT&T, and T-Mobile. And we stopped at this location, and we ran measurements on all those phones, and then we collected the data. And this is another depiction of a measurement effort that didn't happen at the same time. This one was earlier. So you can see Sprint was in here as well. And in this case, we were especially interested in measuring. We had a collaboration with several pueblos, mostly north of Santa Fe. So those are some other, those are also showing you a measurement effort. One thing you'll notice here is it's quite a bit easier to measure on roads, right? You don't see any measurement points there that where we would have to go hiking in the wilderness, to do the measurement. So this is the kind of thing you do. This is called war driving. It stands for something like wireless access. I never remember what the R is. It should be like discovery, but that's what we still have the R. So it's time intensive to do this sort of thing. And I know you might say to yourself, well, like, don't the providers know? Like, doesn't T-Mobile know where the connectivity is? How would they know? They're not going to know. I mean, they know where the towers are for sure. And they know they probably could take customer data and customer complaints to be doing some kind of mapping, but they don't. There's no magic that the providers know that would tell them, especially when you talk about quality. Okay? So there's one thing which is to say, can you get any kind of signal or not? That's a binary, right? Yes, no. There's a whole other level of detail which would be, is the quality here good enough, for example, to make a video call? Or is it only good enough to send minutes on this? Okay. So there's no magic that the providers have that lets them solve this fundamental problem of producing a map of the quality. So we were able to get access to a pretty nice data set, a crowdsourced data set of coverage, meaning, and this was binary, covered or not. Because an alum from Georgia Tech worked for a location services company. So location services companies, they help provide, they build a service which has to do with locating where things are, and then other things get built on top of that service. So I won't go into those details, but what we did was we took some public crowdsourced data on coverage, and then we had this private data set that we had to sign the data use agreement for, and we had some measurements that we had taken. So those were the three data sets in this tail of three data sets. We published this paper in Communications of the ACM. Who gets Communications of the ACM? You get this publication? All the professors and none of the students. Okay, that's normal. So Communications of the ACM is actually a pretty wide circulation magazine-ish thing that comes out once a month and publishes some opinion pieces and some overview, publishes a bunch of different things, including research-y articles, not necessarily super research-y, but research-y, but anyway. So this was a good candidate for Communications with the ACM. And I just want to show you an example of the kind of results, and unfortunately, the colors here are very different than what's on my screen. So anyway, okay, so this is New Mexico. This is New Mexico, roughly speaking. And what we did, and so this is showing two different providers, Verizon on the left, Sprint on the right. And this is for the two data sets, the public one and the private one. And if you ask about any particular geographic location, what we did was we said, okay, in the public data set, does the public data set say this location gets service or not? And covered or not? And then we said, in the private data set, does it say this location gets coverage or not? Okay. So for any given spot, you have two answers, one from each of the data sets. And the color coding here is that all these big purple areas, light purple, that's where both of the data sets said no coverage. Right? Both data sets agree, no coverage. And so Verizon, much better than Sprint. Lots of purple. The green is places where they both said, yeah, there's coverage. Okay? So purple and green, both data sets agreed. But there's the places in yellow, and it says pink here, but it's more, I think it's this darker purple, where they disagree. So both directions. Sometimes the public data set said covered, the private said no. Sometimes the private said covered, the public said no. Okay? So, and not surprising, but interesting. These areas of disagreement often happen in between the areas of agreement, right? So there's a spot everybody said, okay, yeah, this is covered. Over here, yeah, there's no coverage here. the challenge is in what's the data in between the two as you transition from covered to uncovered. And that's why these disagreement areas sort of tend to, it's easiest to see in this picture, tend to follow they sort of color the green, right, where you have it. So this is an example of the kind of analysis we did in that paper. And then we built a prototype to do our own measurements, called HyperNet. And we took advantage of the fact that, because of COVID, we didn't want to meet in person. We built this thing, we did a lot of hiking, camping, and backpacking. This is Baya right here. The smiles are for real. We had a wonderful time. And it was a combination of a chance to get together in person without being worried about COVID and also do some research. So, okay, so that we did that. Now, what happened next? So we wrote a paper, more complete research paper to a conference called Computers Supported Collaborative Work. That's the CSCW. We wrote 2 National Science Foundation proposals to a program called Internet Measurement Research, specifically on Internet Measurement Research. One was about using machine learning to make predictions of the coverage from limited data. The other was about building a tool suite to crowdsource mobile broadband. One of these proposals was funded, and the other one wasn't. I'll let you guess which one was funded. I hinted this, put AI in everything, and your chances will go up. So this one was funded, this one was not. And then out of the blue, I got contacted by the Rockefeller Foundation. So the Rockefeller Foundation is a private foundation. They have money. They give out money by some totally mysterious process. You get on their radar. In this case, the process was they saw that communications of the ACM article. I guess they were trolling, they're like looking around for things to fund. And then communications of the ACM has a lot of credit to it. So they called. And I mean, I fell off my chair. Money doesn't usually show up this easily. So, and then we also had this proposal already written that MSF didn't want to fund. So we turned that into a proposal for the Rockefeller Foundation. And we have been in the process of building up, we changed the name from HyperNet to CellWatch. We've been building up this suite that has as its foundation an Android app for measurements and then a back-end data repository. Working with ML people, we've been working on models to try to predict coverage. And then Baya in particular has been working on a coordination tool for communities who would like to make measurements. And they like to do it in a coordinated way. Like, we might say, next week I have to make a drive, out to Los Alamos or whatever. I can take measurements on the way. We'd be like, okay, great, we don't have enough, we need more data on that path. Or maybe someone says, I'm going hiking in this canyon. Oh, great, you can take measurements there. So you can see that if you wanted to take on that task I gave you of mapping the coverage in a region, you might want to work together with other people. And you might want to measure in places where there wasn't much data. You might want to do it in a coordinated and smart way. So we've been working on this. Okay, so we were working on this. Then along came a lot of money. Not less, but a lot of money. And it's a program called the federal government program called Broadband Access, stands for Broadband Equity Access and Deployment. So the BEAD program, all right, here's the setup. This is the same setup I gave you before, and essentially. Many Americans lack access to affordable, reliable, high-speed internet. The BEAD program, $42 billion with a B for high-speed internet access. And importantly, we prioritize this unserved locations that have no internet access or only have can't exceed 25 megabits per second download, 3 megabits per second upload. And so that's called unserved, and then underserved is subserved. Okay, so there's these non-served, unserved, and underserved. But okay, what does this say? There's this big pot of money. Where's the money going to go? It depends. It's going to go to places where the coverage isn't good. Either it doesn't exist or it isn't good. Well, how are you going to know that? Right? So these efforts to measure and model and predict and map coverage are exactly what is needed to help direct this funding to places where the coverage is not good. So that's exciting. So this is now starting to get to policy, right? This is a statement of policy. It says the government will prioritize this spending to particular places. So that's a policy decision. But it has a technical underpinning, right? So you can say those words, but to make that happen, to be true to that, requires essentially a technical solution and technical knowledge about coverage. Because if you let the providers tell you where they cover, first off, they have some incentive not to tell the truth. And number two, they don't always know. Okay, so there were maps already that the SEC required providers to submit these maps saying which census blocks they covered. There was a weird catch where if you covered one address in a census block, you could count the whole thing as covered. Now, there's some really big census blocks out there. So there were some sort of loopholes and anyway, so the government came up with a process by which individuals could challenge what the providers said. So maybe you were a T-Mobile subscriber, and T-Mobile made these maps available, and you look at the map and you're like, no, I know that when I go to that location, I never get coverage. So challenges could be mounted against what the provider said was data. But then the providers didn't want to have to be chasing after spurious claims, like, I don't know, you could just denial of service attack the provider by claiming there's no coverage in all these different places, and then the provider would have to provide counter evidence. I mean, that is the whole picture here is evidence gets assembled, and then the providers can provide counter evidence, or they can just say, you're right, you don't have coverage. So there's this long document, this Federal Communications Commission document, explaining how these challenges are going to work. And I'm going to read you a little bit of it, but it had to be sufficient measurements to ensure the challenge process is statistically valid, while remaining, in quotes, user-friendly. And it's a good thing they put that in quotes because, in fact, it's not very user-friendly. If it was, they probably wouldn't have had to put it in quotes. A methodology for determining a threshold number of tests and geographic boundaries, and then the challenge, blah, 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 H3 geospatial indexing system, blah, 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 etc. Okay, so one of the things why I grad students is for them to take a 75-page policy document and turn it into a flowchart for determining if you have the data for a challenge. So this is only the very beginning, but you can even see does hexagon H, that defines a geography, have a cognizable challenge? That's the one that the FCC would respect. For a given provider, a given technology like 4G versus 5G, an environment that means outdoor moving versus not moving, direction, I don't even remember what those meant. Okay, so there's this long document that explains how much data of what type taken in what geography will be considered valid for telling a provider you're wrong. And it's not one measurement taken in one location. So then we built a tool that helps you see what data you have. So this is the hexagon gridding of the globe. It's used by Zagura. Hexagon grid, and it has a hierarchy, right? So there's like a bigger hexagon, and inside of that are these child hexagons. And you have to have a certain number of measurements and a certain number of child hexagons. They can only be taken between certain hours of the day, and more than half or something has to be negative. It's a whole bunch of these. So we built an app called Cell Watch that that meets the FCC's requirements for being able to take measurements that can be used in town. And we have very recently put this app through the FCC's approval process, and we know, in part because it was clear we were debugging the FCC as we were developing this, and also because they told us that nobody else, there is no other third-party provider of a challenge app. The FCC paid a company to build it, so there is an app. It's not that there's no app, but the one that exists prior to ours was built, under contract from the FCC. We are open sourcing our app, so you can find out how the measurement works. You can interrogate the code, you can take the code and do something else with it. The company that built the FCC's app, that's a closed system. You can't see how any of the data, you can't see, for instance, how the measurement process works. So we've been on this journey. This is the flow chart to get FCC approval. There's a loop up here that you could get stuck in forever, apparently, right? Unfortunately, we did get stuck in there. Although we did go back and forth a lot with the FCC because they had this big document, and then, as you know, when you read a specification for code, when you read an assignment for code that you're supposed to write, sometimes you have to go ask the professor, like, what did you mean by that? It's not, English doesn't always give you a clear answer. Sometimes there are ambiguities. So we went back and forth, especially about privacy policy. We went back and forth with the FCC a lot. And November 1 was the end of this. You have to have a public comment period. So our proposal was up for public comment. You missed your chance. It ended November 1st. And so we're like in here. We're in here right now. So that is the journey. Okay. This was a journey that started out with some pretty interesting fundamental research questions, like how can you predict, say, cellular quality when you're not going to measure it every day? And then how can you gather more data? Like, can you crowdsource more data? And what are the tools that would make it actually user-friendly for people to do this, et cetera, et cetera. And it ended up in this pretty exciting place where, Google got this app on the Android, available for Android, that meets these requirements. So that was pretty exciting. All right, now I'm going to spend less time talking about my career path to policy. So I started out on a pretty normal path. So I was hired as an assistant professor in 1993. I got tenure, I was promoted to associate professor in 1999. Then I had a very weird experience. This is quite uncommon. We had a dean leave, and they needed somebody to do the job for a little while, not for too long. And strangely, they asked me to do it. The professor delivered, no, this was super odd. Like, I was not a full professor. So, and then we hired a dean, and I became an associate dean, full professor. I was the chair of the School of Computer Science. I was involved in the Georgia Tech White Big Thing. So I did a bunch of things. And then I was getting a little bit bored. And I really wanted to be in some kind of leadership role. I actually applied for a dean job at Georgia Tech. I didn't get it. And so I was like, okay, I feel like there's not that much left for me to do at Georgia Tech. So I applied for 3 jobs. I had previously applied extremely sparingly, like to a very small number of jobs, because I was pretty happy. But I applied for 3 at the same time. And one of them was to go to the National Science Foundation. And that's the one that I took. So the National Science Foundation is the part of the federal government that funds the vast majority of computer science academic research. They fund other things as well, so there's a biology part, there's a math and physical sciences part, there's an engineering part, so they don't just fund computer science. But for computer science, they're an incredibly important funder. And they have both permanent people who work there for a long time, and then they have rotators, which is what I am. So I'm on loan from Georgia Tech for up to 4 years, working for the National Science Foundation. This is my first day of school photo. Somebody was walking their dog, and I was staying in the Airbnb, and I said, "Will you please take the first day of school picture of me on my first day of NSF work?" You know, when you've had one job for 30 years, it's kind of exciting to have like a first day of work. On the right-hand side is a little library. You guys probably have these little libraries. This one happens to be at the Finnish embassy from Finland. One of the things in my portfolio at NSF is advanced wireless programs. Makes sense, right? That's part of my research interest. And Finland is very interested in future 6G, future 2. I could have gone to Finland 3 times in the first 2 months I was there. They kept inviting me, and I kept saying, "Sorry, I don't want to take the time to go all the way to Finland." And finally, I was like, "I'll go to your embassy," right? So that was my trip to Finland. I've gotten to at least rub almost shoulders with some famous people. Neither of these pictures of famous people are probably you would probably guess. Anybody know who either one of these pictures is the one on the left, few of the faculty money. The hint is PBS. That's Amna Nawaz. That's pretty. If you know who Amna Nawaz is, this is like a big deal. Amna Nawaz is big. She's a news anchor for the PBS NewsHour, and she was on a plane in the same row as me. On the right-hand side, you can't really see it very well at all. There's a tent, kind of a tent down there. That's because J.D. Vance lives in that block, and I'm on the driveway of the house where I rent a room in Alexandria. So J.D. Vance lives on my street. I saw his wife in the coffee shop across the street. I've gotten to do a bunch of things that are out in the outreach category, especially trying to connect with people in export states, which you are, and minority serving institutions, which you are, to encourage and try to support more NSF proposals, because we're really trying to expand our geographic outreach. So I got to go to Alaska for an outreach trip, and I wanted to have an Alaska experience, so I went on a sled dog ride. I have found it to be incredible. The people there are just amazingly committed to the work, and just wonderful to work with. So this isn't going away. This is a retirement party for Darlene Fisher, who really about single-handedly was responsible for networking research in the U.S. with NSF for more than 30 years. Yeah, pretty amazing. Okay, I think actually I'll stop now and ask for questions, because I'm going to keep to the script time. We have not too many minutes, but a few minutes for questions. So yeah, thank you.
So, say you were, your goal kind of was to provide cellular data for everyone. Is that just in the U.S. or worldwide?
Yeah, so that's a great question. We have not, except for a very limited test, we've not tried to use our tools outside the U.S., but we don't have any reason to think they would not work. So to say that without two negatives. We think they will work. And I had a grad student doing some field work in Madagascar, and he tried it out, and he was able to take measurements. So there's nothing cooked into the tools that's U.S. based. Now, federal U.S. FCC doesn't care about coverage anywhere else in the world, right? So that there is some, so that's the yeah.
So, I don't know if you mentioned this, but has your work been used to expand coverage in areas that are?
Yeah, so that's the downstream hope. I cannot point to where that has actually happened yet. These are that kind of thing takes a long trajectory, but being able to provide an app that people could use to launch these challenges, in terms, this isn't going to sound like a short path, but it's a viable path, right? That then the providers find out that their coverage wasn't good in a place, and they get funding and they build an app. There's a, I don't know whether you're called cynical or not, depends on how you think about things, but you could say, well, this challenge process is a great way for providers to find out where their coverage is. Like, you've essentially crowdsourced, you've told people, well, if you don't think the coverage is good, go take a measurement. And then, whoa, that's awesome. Now we know where our coverage is because you just told us where it is and where it isn't. So there's a really plausible path here from measurements that contradict what providers are saying to funding and providers making that doing build-outs. It's not a tomorrow thing, it's not a next month thing, but it is a path. Yeah.
With that in mind, have you noticed a positive trend towards consumer protection with these things, or is that another battle?
So, it depends a little bit what you mean by consumer protection. I do think that, this commitment of money has really focused attention on the fact that these maps of coverage are very incomplete. There was Congress ordered the FCC to have accurate maps. It's like, I can order you to, get an A in math class, it doesn't mean you can do it, right? So that's sort of comparable. Congress said, FCC, you are responsible for having accurate maps. And as I mentioned before, there was this method, one of the ways they did that was they asked providers to provide the data, but that had some flaws. Now that there's, they're talking about real money and wanting that, this is our money, right? This is taxpayer money. We want it to be spent in places that are going to expand the footprint of coverage. We don't want these providers to just take the money and, do something, for instance, create faster connections in places that already have pretty good connectivity at the expense of expanding the footprint, right? So, the consumer protection agency, that's a whole other world, but some amount of sort of honesty and, for instance, that's like what they advertise over their speeds. That's maybe also something you're getting at. That requires measurement also. Yes.
So I understand that it may be useful to know how good the cell network coverage is in various places. If the goal was broadband internet, isn't the alternative, which you mentioned earlier today, Starlink, simply better than anything like this?
Okay, so the question is, to paraphrase, doesn't satellite internet solve the problem? Doesn't satellite internet give you connectivity everywhere? It absolutely provides a coverage footprint that cannot be achieved by terrestrial or cellular. The quality is not great, so there is an issue of satellite internet as your method may get you the binary coverage, which in many places would be a big, would be an improvement. the quality matters too, right? So, like I said before, can I do a video chat with a doctor, for example? Can I, or can I just send an SMS? So quality matters, and as we talk about overall equity, we really like to bring up the four as much as possible on the quality. And satellite will play a role for sure. And it does make some coverage, you get a huge number of advantages by having such a large phone. But on the quality side of things, it's a little bit of a mixed picture. Technology.
So this process of taking the FCC policy and turning it into code, that seems like a really great way, you mentioned running the policy, or like plan out the policy if possible,
Right.
things like that. It seems like that in and of itself would be a great thing to do with government policies. Is there any effort to do that in other spaces?
Yeah, I think security is probably the other space where, policies get written and whether they are like internally consistent or typical, right? So I think that's, security policies is a big space where, at least, that's where I would look to. I was really proud of this book chart. Like, that thing takes up multiple pages. And that distillation on its own is valuable. If somebody else wanted to code, that would be a great starting point. What did you want to ask?
I mean, following up on some of the student questions, and those, so can many of us in New Mexico, a very rural state, often struggle with cell phone problems? Can we use your tool to kind of file complaints, for example? And would we do that in an individual manner or?
Right. So can you use so much to, so the answer is very soon, yes. And you actually don't have to do an information. You can just independently make measurements, and on the back end, the SEC will figure out if you met the criteria. The downside of that is your chances of meeting the criteria when if you're going to rely on this sort of, you might take a look at the specs and figure out that, you need it yourself to take a bunch of measurements in a confined geography, and then that would greatly increase the chances that on the back end, you had actually stumbled across or assembled the challenge. The coordination tool has been an interesting, I think it's an interesting research direction to think about how it might support communities that wanted to do this. It's much earlier, and I'm not going to give you the coordination tool. But the FCC will on the back end construct challenges out of the data. But you take one measurement on the you're never going to add up to a challenge. Yeah.
With that in mind, you've mentioned that it's an Android app, and I just looked that there's not an iOS one. And I'm curious. My question is, do you intend to do that? Because Apple has a monstrous market share.
We would like to. There's two things that are standing in the way. One is money, and the other is developers. I had a master's student, he was in a PhD program, who did most of the cell watch code development. He decided to leave a master's degree. It's just very hard to get development done in a university that's going to be able to withstand, kicking the tires. We would really like to build an iOS. iOS is more, you don't have as much access to the low-level data, so that was why one, and also kind of Android's open nature, those were two why it started. Yeah.
I don't know if universities have like cross collaboration with research like this, but if you didn't get the money, would you look into something like that? Just to have those researchers.
Yeah, I'm in the process of trying to figure out if I can hire this get this master's student to take a job with me instead of going to a software development job. If he will stay, I, I will go back to Rockefeller and ask them if they would fund the development of an iOS version. And I think there's a reasonable chance that they would say yes. But to be honest, I found it rather stressful trying to deliver code into the real world using grad students, using students. Because just how other things going on and graduating and stuff like that. So I'm not super, unless I think I have a good path, I'm not eager to promise that without it being clear to me. Yeah.
Curious, how do you validate that the information you're getting from it actually is accurate?
Yeah, that's an awesome question. How do we know that it's accurate? So I have a collaborator at UC Santa Barbara. She's had a master's student who's taken a bunch of network measurement tools. So it's not, when I said that we thought we were the only third-party app, that was the only third-party app that meets the FCC requirements. There are probably do speed tests. Some of you will do speed tests before. There are other tools for measuring the quality of your connection. They just don't meet the FCC's requirements. So a collaborator has had a master's student who downloaded 4 or 5 of these tools and has been running controlled experiments. They don't all give the same answer. Which is actually not a surprise. The FCC has their own tests for the quality, which they are going to run now that it's been through the public comment period. There isn't. We could set up something where you have some confidence in ground truth value, but especially for mobile, it's very hard to. You're really comparing. See if multiple tools give something in the same bar. One of the things that makes the measurements different is that, okay, let's say who's taken a networking class? Where's the socket program? Okay, so if you want to measure the download speed, what are you going to do? Download speed. Yeah. Are you taking a networking class? No. Okay, how should we measure the download speed? Here I have a device. Okay, first off, I probably need to do a download, right? And measure it. Okay, so if I'm going to do a download of a file, where should I get the file? Right? I need a server somewhere. I need a server somewhere that has a file that's big enough, and I'm going to download from that server. Okay, but now this is a little hard because here I am just with my phone. So I would. Maybe I could go to like a standard, I could figure out some file on some server that was public. So that's not what happens. That's not how these measurements, that's not the most robust way to run these measurements. The robust way to run these measurements is you have a collection of servers that you control. And those servers are sitting there waiting for measurement requests. And when the phone contacts the server, that server, which you control, starts downloading data, and it can measure the download, while the phone can also measure the download. If the server is very close to your device, meaning in the network close, we will get higher download speeds than if the server is far away. There's 2 reasons for that. One is, if it's further away, you have more network links you have to traverse, and the chance that one of those is technically constrained will be higher. The other is, even if that doesn't happen, it turns out the way that TCP works, it depends on the round trip time. The round trip time helps determine how quickly the download increases its speed. Okay, so TCP, which is fascinating protocol. If you're close by, you'll speed up faster than if you're further away. So there's a company that has measurements, and they have contracted to put their servers co-located in many, many ISPs. So if you use Ookla for measurements, you get faster speeds because they're connecting your device to a closer by server. So in order to build our app, we had to also have a collection of servers. We absolutely did not want to stand up and manage a collection of servers. So we're using a facility called a measurement lab, MLab, which is available for public experiments. They have a collection of servers worldwide, but they're not as densely deployed as the Google servers. So we're not surprised that we see differences. But your question, this question could address this question. This question is a like extremely fascinating question. How would you know if your measurements are right? Okay.